There's our company symbol. There's a good old patch. This is for on the road, so we'll show you how we get in our new air-conditioned bus here. That's made out of aluminum, and it has everything. And even for long hole count holes, I believe they put a stove in there. I guess that's a lot longer than I'd care to hold for, but this is your standard engine light off, and it sure is. It's different in one respect. The engines come up to speed. You feel that noise in the cockpit quite clearly. It's things are shaking, mostly your knees. The bolts blow right here, and this is a beautiful shot right here. It's one of the prettiest liftoff shots I've ever seen. It clears the tower, and I always say it comes very close to the edge of this thing here, but it misses it every time, so I guess that's all right. One thing that was different on our ascent was our 15 degree per second roll rate. It's a real high roll rate. We rolled it to 135 degrees. You wanted to get up thing pointed in the right direction before you had to encounter load relief. And of course it rolls around and completes that roll within, before it's starting to do 300 knots. Our max dynamic pressure equivalent airspeed, for as an example, 466 knots. This is taken from the chase plane, and she's starting to climb straight up. They'll defocus and refocus this thing, and you can watch it go supersonic. Look at those shocks come off there. The vibration and the noise picks up when you go through dynamic pressure in a way that I don't remember on STS-1, but because the seats were pinned down, there's a lot less vibration. A lot less, and it was really a nice ride. Add anything to that, Brewster?
Well, it really put you back in the seat right away. It kind of surprised me. The G's are on you real fast. Here's a good shot of the SRB SEP, and when that happened, we got a lot of material over our front windshield that kind of surprised us a little bit, but you could see through it later on when you needed to. We finally made it to orbit and opened up the payload bay doors and deployed the radiators and put out the KU band antenna, and we were ready to operate in a really short time. And this gives you an idea how easy it is to get around in there. You just float in and out of the seat, and this is a configuration on orbit with our little computer that told us where we were in the world, and one CRT running most of the time, and alone on the flight deck while the other guys are busy doing science. And John's taking pictures out the window there with a 35 millimeter camera and a 105 millimeter lens on it that we borrowed from the guys in back. And once we got the hatch open, the science crew started heading back to the space lab to crank it up, and they'll tell you about that.
Here we are, we're just floating back to open up the space lab hatch and now enter the space lab for the first time. And it was just the way we left it on the ground, not a thing had come apart, and it looked almost like home, just like our trainers would have been over at the Marshall Space Flight Center in the payload crew training area. And felt very, very comfortable moving on in here and beginning to activate the space lab. Have a few valves to throw and various pieces of equipment to turn on. And let's see, I guess we're just going through some...
Sal.
Oh yeah, this is SAL operations here. Scientific airlock is about a 1 meter aperture that we first of all opened up the lower hatch right here, and then we cranked the table down, which we'll see turning on that handle in the upper right hand corner, and this lowers the table down into the module, and then we can take off some grounding straps for necessary there for launch that you can see coiled up right on the front, and then begin to mount our experiments to it. And so that's the table on which we extended two different experiments into space. One of them associated with a Japanese experiment had diagnostics equipment to look at the plasma surrounding the vehicle. And then the other one was a very wide field camera to take photographs of the stars in the ultraviolet. And so we've now in the process of closing it back up, putting the lower hatch, the inner hatch, back onto the scientific airlock. And then after that's completed, we would open the outside hatch and extend the experiments on into space. It's very easy to move that lower hatch around, inner hatch, in weightlessness, much better than it is on the ground. Here's a view showing the outside hatch now opening up to expose that 1 meter diameter chamber. And after the outer hatch is laid back, fully 180 degrees, then we'll see the experiment table with the experiments on it, then cranked out into space. And the first thing that we're extending here is the diagnostic package for the Japanese experiment. And that can then be exposed to the plasma directly out into the environment and measure what's going on. Here's just a brief glimpse showing ham radio or amateur radio operations. Looking out the overhead window and holding the little transceiver unit just about the size of the portable walkie-talkies that we use for communication within the spacecraft. Slightly different power level, slightly different frequencies, about the only difference. And on that, we're able to communicate all around the world. This is a shot from the inside the space lab, just showing work at a couple of our computer keyboards. We have one computer keyboard on each side of the space lab interior, and then a number of experiments. That's a Japanese experiment showing a plasma jet. Those pulses come out at about every 15 seconds or so, and we can look at vehicle charging effects and interactions with the medium around the spacecraft. Several of the experiments have panels adjacent to the computer keyboard. One of them, again, it's a Japanese experiment, has a television tube. This television camera is what we're looking at here. We're just passing the Earth's limb. That's the air glow at the edge of the Earth's limb. And the camera is now swinging up to look at various stars. The stars are a little bit out of focus here because the camera is purposely focused at a distance of only 10 or 20 meters so that we could see some of the nearby emissions from a spacecraft rather than having to look out at infinity. These are cloud lightning disturbances at night. So this is the dark hemisphere of the Earth. We're seeing lightning discharges in the clouds here in the center part of the picture. That's the Earth's limb off to the right with a star over at the very right-hand edge. So we're now doing more experiments on the inside. Why don't I turn over to one of you fellows to continue? Continue the narration here.
On the left side of that video picture here, you see the fluid physics module, which is a machine to study the behavior of liquids under weightlessness conditions. See it here, it looks a little bit like a Fiat engine. The idea is to understand liquids because all the material sciences experiments like growth of single crystals or the production of new alloys deal with liquid material, with liquid metals. And that machine allows us to use silicone oil as a model. You see here a liquid column. In this case, we heat one side of the silicone oil, and you see flow patterns inside. Look at the little tracers. And that phenomena is called Marangoni convection. It can be observed only in space because it is masked on the ground by the standard convection, which is gravity-driven. The Marangoni convection is driven by a difference in surface tension. That is another experiment. See that little tank? It is partly filled with silicone oil, and it is used as a model for rocket tanks to find out how the liquid behaves inside a tank. That is a simple sphere, just water sphere, and I'm pinching a little injection needle in it, and I'm trying to put an air bubble inside the water bubble. And see how it moves inside, and you can also create all sorts of oscillations. It's very spectacular, and if you leave it on its own, it is really an ideal sphere. I think it is impossible on the ground to make a sphere like that. Here I'm checking a few temperatures. That is the mirror heating facility. We had a little trouble with its cooling for a while. There was probably some air in the water loop, and I think I hand over to my partner, Bob Parker here. No. Oh, no, it's Byron.
Okay, well, I'd continue. This is a silicon rod in the mirror heating facility. We are melting it, and we are regrowing the crystal in space. We got the rod from the Earth. It was a single crystal, and we are now growing it. The shiny area in the middle is the molten part of the crystal, and the furnace will slowly travel along the rod.
That is one of these liquid bridges.
Right. The objective there is to get a dislocation-free crystal in space. Here's Owen being a subject in one of the many life sciences experiments that we've done. This is called the hop and drop experiment. It's designed to look at the influence of the vestibular organs on the postural reflexes. And we measure the muscle signals in the lower leg. If you look at Owen's left leg, you'll see electrodes and cables down in his lower calf. Another part of that experiment entails hopping. Again, we're looking at the muscle responses. These are primarily generated by the vestibular system, your organs of balance in your inner ear. The small box that we've had on our head is an accelerometer package. Here we're showing a rotating dome which is trying to investigate the visual vestibular interaction that occurs either on the ground or in space. Here's a good picture of an eyeball. You can see the reflection of the rotating dome actually in the person's eyeball. Shortly we'll see a picture of the eyeball with a contact lens on it, and you'll be able to see the movements, the rotary motions of the eye quite a bit more clearly. There you can see the lens as the eyeball has torsion to it as we try and track this rotating dome. Contact lenses are very interesting. We can get them to stick very nicely even in a weightless environment. Makes the data analysis much easier. It's a very impressive thing to put your head inside this rotating dome, and contrary to earlier predictions, it is not provocative in space as long as your head is fixed. Wolf, why don't you guys talk about... I guess I'll continue on. This is another vestibular experiment. We're looking at a person's eye motions that are driven by the vestibular system. So we spin somebody around, stop them abruptly, and watch the decay of the eye motions. Just to show that we really were in zero-G, it's much easier to do this type of maneuver from the ceiling. So we're actually hanging up on the ceiling with our feet in the handrails and able to get a large rotation. Wolf?
There is another biomedical experiment. It deals with the pressure waves which go through your body whenever the heart contracts. If you stay calmly on a sensitive balance, you see the needle a little bit flickering, and that experiment is really a good one to be conducted in zero-G, because then there is no gravity force which is superimposed on that waves. And what you saw me doing here is to speed up my heart to give that guy also measurements at high heart frequency. It's probably Bob who can comment on that one.
It is a part of the European vestibular experiments that Ulf and I took part on each other. In this particular one, we're looking at thresholds, determining how low an acceleration a person can feel. See right there, a very low acceleration, trying to see if one can detect it. We did this in all axes.
Subject.
It's there, the x-axis. Now you can see very simply the person who is controlling it in the background. It just flips him over and starts, and you'll see in a minute, do it in the y-axis. It's very subject. You just strapped in, very relaxed. In fact, one time Ulf almost fell asleep, and we had to shake it hard enough to wake him up, I guess.
Yeah,
you see the very small motions that you can detect.
It feels like sitting in a comfortable rocker chair, and it's no wonder if you fall asleep.
It's John coming down to visit and see if we're doing enough work, I guess.
Every time I came down there, they wanted to draw my blood, so I had to leave.
This is the sort of trip we make back and forth many times a day between the middeck and the space lab. We are going out to the middeck, passing through the tunnel adapter into the airlock, and coming up into the middeck here.
That is really a fun trip, too.
Supper time.
See, it doesn't make any difference whether you're upside down or right side up. Isn't that nice?
Now it's John upside down. I heard the question. Rooster, Robert.
That looks like
This is an evening's relaxation where the red crew was coming off shift. We decided to come down and bother the blue crew who was starting to try and do some work.
Notice I was working, and they made it look like so much fun that I had to stop.
It's a great zucchini acrobatic team, actually. It's process here for about 5 seconds. There's a lot of volume in that space lab. It really is nice. See, when you've been in space a little while, down is up and up is down. It doesn't make any difference. It really doesn't.
Here we are at the end of the mission, taking off the magazine off the large format metric camera, and this is a TV shot we made looking up from the floor, again looking at the problem of moving large objects in space. As we basically demonstrated before on Skylab, but people always continue to worry about it. You can move an object almost as large as you wish, as long as you just move it slowly. As long as the accelerations are small, we had no problem controlling and moving very large objects. See Byron here moving a fairly large drawer just up to stick into a cabinet and close it. It's a lot of these things just ran and slid and moved very nicely and freely in space. You see there, just up it goes and it's shut.
It's time to close the scientific airlock. You can see us view out the aft flight deck window as the table's already been moved inside and the hatch is coming down.
And here's the entry join up. Charlie Justice in his chase plane is joining up. He's getting better and better at it. And it's a beautiful day out there at Edwards. We could see the lake bed from 60 miles out and had no doubt about where we're going and what we're doing on the flying end of it. Because of our problems, we'd been up for a long time. Brewster had been up about 14 and a half, 15 hours. I'd been up about 20 and a half hours, I think. And even so, because we've had a lot of practice doing this kind of thing, it just seemed like old home week, getting back there and shooting those approaches, shooting that approach. See the shallow glide slope? We're on a 17-degree, 17-degree glide slope. It's really a shallow glide slope. It's hard to believe that the orbiter right there weighs almost 110 tons, but it does. And it's coming down and just working beautifully. The orbiter has a lot more precision, crisp handling qualities in the real vehicle than we've been able to do in some of our simulators, because it would take a really super actuator to make those crisp motions. And it's very straightforward. We're a little low on energy, so Brewster held the gear down to about 250 feet. But the gear still comes down, locks in about 5 seconds, 6 seconds. And the ground effect model, we've never really, it's tough to simulate it just properly, but the ground effect model really cushions this baby with this big delta wing. It just cushions it beautifully right into landing there. It looks like about a 12-degree angle of attack. And straightforward landing and roll out. I think the lake bed must have been still wet a little bit, because we really decelerated rapidly. We weren't using very much brakes, and we rolled a stop 10,200 feet from the threshold, which with that big payload would at least show us something about our capability into abort fields around the world, which are a little shorter. If you look real close, you can see a little bitty nose wheel steering test in there somewhere. It's kind of hard to see from this angle. Yeah, but it's there. It sure is a delightful flying machine, start to finish. And like I say, it weighs quite a bit, and we proved the capability to bring back on that mission over 21 tons of payload in vehicles like the Discovery. We also looked at a new flexibility and coming in over the poles almost. We're over the Aleutians and Sakhalin Island in that area. Now here you see 6 men getting off a spaceship after 10 days in space. They haven't had a bath. You might say this is 6 dirty old men, but and they probably really are. Looking forward to a shower. And I think they're pretty darn steady considering how long they've been up there. This is a PAO that shows how we're going to carry this on around the world tour, and we want to make sure all the, if we ever go on this around the world tour, and we want to make sure that all these people get to see their own flag. And this is an outstanding bunch of people, the Flight Control Division and the Entry Flight Control team that did that job and brought us back home safely.